computer science. So I'll leave it to Professor Sipser. So thank you for being here, and you can start.
Sounds good. Thank you, Brian. And welcome everybody to this, I guess, the 6th lecture. I haven't seen the other ones of your Everrays experience. I am going to talk about a problem that's in the overlap between mathematics and computer science. It's actually one of the most famous problems in mathematics of our time. And it has to do with how fast you can solve problems on a computer. You know, as we know, computers are very, very fast, but there are still some problems which take a long time. And I will give you a sense about that I'll give you some examples, and then we'll explain the problem. And this is a problem in mathematics, by the way, that's unsolved. This is a very famous unsolved problem. So if you're interested in math and working on challenging things, I wouldn't recommend starting with this one, but at least this gives you a sense of the kinds of problems that many mathematicians have been interested in. Okay, so let me start off with just give you some, starting slow. I'll give you a simple example of a kind of problem that you might want to solve on a computer. Okay? Well, this is a very easy one. Just 7 times 13. Obviously, you could do that in your head, I hope. But it's a problem, just as an example, of what we call multiplication. So this is the multiplication problem. I give you 2 numbers. I want you to multiply them together and give the answer, which in this case is 91. So that's a pretty easy problem. Let me give you one that's just a tiny, tiny bit harder, which is going to be the reverse of the multiplication problem. Here I'm going to give you what we know was the answer from the last slide, the number 91, and I want you to come up with 2 numbers that multiply together to give you 91. Now, of course, you could remember from what we said from the previous slide, but let's say, just imagine for the moment we're starting afresh. I give you number 91, and I want to know what numbers you have to multiply together to give you that result 91. So we also call this this is a well-known, well-studied problem in mathematics. It's called the factoring problem. I give you a number, and I look for the factors of that number. And so in this case, the problem is number 91, and the answer is 7 times 13. Okay, so that just sets the scene. We have on the one hand the multiplication problem, and on the other hand we have its reverse, which we're going to call the factoring problem. Now let's look at a somewhat larger example of multiplication and factoring problems. So here's a bigger example. Probably not one that you're going to do in your head, at least if you're a normal person. Suppose for some reason that there are reasons why you would care about this. You want to multiply 2 very, very large numbers together. Now that's still something one could do. You could take those 2 numbers. You could take the procedure that you learned in 3rd grade, and you would spend a bunch of time, and you could just go through and do the multiplication. You come up with the answer that I've written in red at the bottom of the slide. Of course, you might also use a computer to give you the answer, and then it's just a matter of typing those 2 numbers in, and then once you push multiply, the answer will pop out in less than a second, because computers doing the same procedure that you learned in 3rd grade, but they would do it very fast. It doesn't need that much time to carry out that procedure. Okay, so that's the multiplication problem again with a bigger example. Let's also look at a bigger example for the factoring problem. Now, we're going to take that number that I wrote on the bottom here, and that becomes the problem. Again, now, let's imagine that we didn't see the previous slide, or we don't remember the previous slide. And now I'm going to give you that number that we had at the bottom, which has 193 digits. And I want to know, what are the factors that multiply together to give you that number? Now, this becomes a problem that is now becomes a challenging problem. If you're going to do that in pencil and paper, that's going to be hard. So you think, well, why not use a computer to solve that much bigger factoring problem, which you can do, and in fact has been done. Somebody took that big number and went through the effort of finding the factors. So here are the two factors that multiply together to give you that number in blue. Now here's the important difference. Even using a computer, this problem took a long time to solve. In fact, it took 33 computer years of effort to find the answer. And the reason we know that is because somebody actually went through the trouble to do it. They didn't spend 33 years. They did it on a parallel computer. In fact, it took 5 months on a computer that had 80 parallel machines. So if you figure out how many, if you multiply that together, it ends up being 33 computer years of effort. That was back in 2005. Technology has improved somewhat since then, but still it would take a very long time to solve this problem on a computer. And somebody actually went through the trouble to do it anyway. Why did they invest so much time? After computers are expensive, 5 months of effort on a big parallel computer is still worth something. Why would somebody spend so much time and do that? Well, in fact, in this particular case, they won a prize for factoring that number. It was $20,000. So they actually got $20,000 for finding those factors. You might think, well, that's a good deal. $20,000 for factoring a number. How can we get in on that deal and factor other numbers, maybe also get paid money to do that factoring? Well, in fact, here's an example of a number where someone had offered $100,000 to factor that number. Now, this is a number. It has 309 digits compared with the one from before, which had 193 digits, a much bigger number. And this number here, the factors are not known. No one knows what the factors are. So if you come up with the factors of this big number, you will be the first to know those factors. Someone had offered a while ago to pay $100,000 for it. And I think, well, first of all, before you start getting out your computer and programming it up, I have to let you know that that prize was withdrawn. So it's no longer being offered. So don't go around solving it and then coming to me for the $100,000. It's no longer available. You're too late. They just stopped offering that bounty, even though the number still the factors are not known. Now the thing is, mathematicians are still interested in factoring big numbers. You might think they're doing it for fun, or they're doing it to understand factoring better. But anyway, who was offering those bounties for factoring big numbers? Okay, I don't know why. I got muted there for a minute. Okay, so why who's paying money to factor big numbers? Well, some of you may know the factoring problem is related to the problem of sending secure communication, doing encryption. There is some sort of background noise, so maybe all of you should be muting yourself except for me, so that there's no background noise, because I think that's I'm hearing keystrokes. Now okay, so why were these prizes being offered to factor? Well, because, as some of you may know, the factoring problem is related to this encryption method called the RSA code. And the RSA company, actually, at the time, was offering money to understand how easy or hard it might be to factor big numbers, because the security of the code, of the RSA code, relied on the difficulty of factoring numbers. So if someone out there found a way of factoring big numbers quickly, that would break the code. So they were trying to keep their finger on the pulse of factorization by offering bounties for people who could factor big numbers. Now, since then, the field has matured. They're no longer offering those prizes, but mathematicians are still very interested in the factoring problem, and whether you can do it more quickly. Now, why is factoring apparently so hard to solve compared with multiplication, which you can solve so easily? And the reason is that the only obvious way to factor big numbers involves trial and error. So if I give you a big number and I want to find the factors, the thing you can do is just try dividing by possible factors one after the next. You can divide by 2, you can divide by 3, you can divide by 4. Well, it turns out you don't need to. You can only focus your attention on the prime numbers. So you can go from 2 to 3 to 5 to 7, and you divide the number you're trying to factor each time by that candidate. And if it ever divides evenly, then you know you have found a factor. If it ever divides without a remainder, then you know you found a factor. But the problem is that when you have numbers that you're trying to factor, which are very large, like having hundreds of digits, then the space of possible factors becomes so enormous that going through a trial and error procedure, or as we call it, brute force search, just searching through for the answer, is going to take a very long time, because the number of possibilities that you have to search through is just enormous. It's just vast. And so that's just going to be a very slow method. Now, from a theoretical standpoint, you might ask, what about trying to find a more efficient way to factor numbers? Instead of investing all that effort in the trial and error brute force search approach, maybe we can find a method, a formula, say, for factoring big numbers that'll make the answer pop out, make those factors pop out without actually having to search for them. Okay, that would be fantastic, because it would allow us to eliminate the search when you're factoring. Now, the thing is, no one knows whether that's possible. It's conceivable that the only way to factor big numbers is to use search, and therefore factoring would be an intrinsically difficult problem to solve, even for a computer. And that's at the heart of what our problem what we're going to be talking about today, is problems that can be solved by searching, but that's very slow. So we want to know, is searching really necessary? Or maybe there's some way to avoid the search and solve the problems more quickly. That's a fundamental unsolved question in mathematics. Whether searching is necessary to solve the factoring problem is something we just don't know the answer to. And this is a pervasive notion. Searching comes up in many, many other problems too that you might want to solve, say on a computer. Let me give you another example, which looks very different from the factoring problem, which we're going to call the clique problem. So the clique problem is here. I'm going to give you a network of these nodes and lines connecting the nodes. Sometimes we call it a graph. And you might think of these as representing, for example, members of your family, or members of your immediate family anyway. So these nodes are the members of your immediate family. And, as we all know about families, not everybody likes one another. So we're going to just put an edge connecting two of these nodes representing people in your immediate family. We're going to put a line connecting them if those two people actually like each other. So so these two people like each other, but these two people here, if you can see my pointer, I don't know if that comes through, I hope it does, but these two people here don't like each other, according to this representation. Okay, so now say you want to throw invite a bunch of members of your immediate family over to your house to have a dinner party. And of course, you don't want to have conflict at your dinner party, so you're going to only want to invite people over who like one another. And, say, for example, you might want to invite these three people over, in the upper right here, that triangle people, because they all have connections showing that they all like each other, but you would not want to invite these three people over because there is a lack of a connection between some of those people. And so they may not like each other. And so the computational problem is I give you this network represented as these nodes and lines, and now I want to find how big a group is there of nodes that are all connected to one another. We call that a clique. So this is a 3-clique here. So like these three nodes form a 3-clique. Here's a 4-clique, for example, if I take these 4 nodes here, they're all connected to one another. The question is there a 5-clique in there? Well, it's not so obvious right away, but, if I kind of highlight it, these 5 nodes actually form a 5-clique. Here, I'll give you darken the edges just to help you see it more clearly. Now, in general, if I give you one of these networks, so here's a slightly larger one. Maybe you have a bigger immediate family. I give you a slightly larger clique, and now I want to find. I give you a slightly larger network, and now I want to find. How can I find, say, a clique within that group that has 8 nodes? Well, you might imagine feeding that problem into a computer, but the only known method for solving these clique problems, again, relies on searching for the answer. You can start going through every subset of nodes, of 8 nodes, one by one, and seeing if all of the edges are present so that now you have a clique. But as you start thinking about larger and larger networks and looking for larger and larger cliques, this is going to become a very slow process because the number of subsets that you're going to have to look through just grows exponentially. So the largest clique, when you have hundreds of nodes, might actually take you centuries of computer time to find just by searching, because brute force search, again, is very slow. Now, the question we would like to know is whether searching is actually necessary to solve this clique problem. Or is there perhaps some more direct, much faster way that avoids the searching? So is searching necessary? Again, we don't know. That's an unsolved problem. Now, both the clique and the factoring problem that we discussed at the beginning are both examples of what we call needle in the haystack problems, where you're looking for a solution, which in the case of the clique would be that collection of nodes all connected to one another, or in the case of the factoring problems, that factor, you're looking for this object in a large space of possibilities. So that's what we call a needle in a haystack, because you imagine you have this haystack, and somewhere in there, there is buried this thing you're looking for, but you have to look and look until you maybe found that needle. Kind of abstracting that a little further, here, if we imagine, here's our haystack, as I've pictured. And now you'd like to know, is there a needle? Or can I find the needle? And you want to know, do I have to search for it? Or is there a faster way of going through that haystack that avoids searching for the needle? Can you come up with that needle more directly? Well, searching may not be necessary in this case if you have a magnet and the needle is a magnetic needle. Because then you can just bring your magnet over and the needle will just get pulled right out. So this is an example where you might be able to avoid the search, at least in this in this sort of analogous kind of problem. And what we'd like to know, say for the CLIQUE problem or the factoring problem, is whether there's some kind of mathematical analog to that magnet. Okay, because having the magnet would allow you to avoid the search. And this is a widespread phenomenon that comes up across many problems in mathematics, broadly in science, and also across engineering and in other fields of human endeavor. So, for example, if you're trying to schedule meetings or Zoom meetings or Google Meet meetings or whatever, and you were trying to have a large group of people in your ever-raised community there, and you're trying to find some set of meetings so that people don't have conflicts. You might go through all the different possible schedules, but because there are so many, that would take you a very long time to do it that way. And you might want to try to pack boxes into a large carton. There are many different ways of packing those boxes. Again, you can do it by a trial and error approach, but whether there's a more efficient way to do it than that is not known. And there are many, many other examples, I won't go through them all, where people can solve problems using search, and they would love to be able to avoid the search because it's so slow. But no one knows whether you can avoid the search. We're going to call this problem of whether searching is actually necessary the P versus NP question. Okay, which informally says, can we solve these problems which seem to involve searching? Can we solve them all without actually going through the search? Can we solve these apparently search problems in a more direct way, which would be faster? Now, the term P versus NP, maybe some of you have heard of that before. It seems like a somewhat strange way to refer to this problem about searching, but that gives us a mathematically precise way of capturing this informal notion of what we mean by search problems and searching for the answer. And so let me just go through that quickly. But this is not I'm trying to do this at a high level, and so it's not absolutely necessary that you follow what I mean by P and NP, but just to give you a flavor for where this is coming from. So P and NP are two classes of problems that people who study this field, called complexity theorists, have named, where P stands for the polynomial time solvable problems. Those are the problems where the amount of time you have to invest in order to find the solution grows as a polynomial, like n squared or n cubed, in the size of the problem. In contrast with a problem where you might need to spend exponential time, which is typically what happens when you have to do a search. That's much worse than polynomial time, because then when the problem gets slightly bigger, you might have to spend twice as much time to solve it, even for a small increase in size. And that doubling and doubling and doubling as the problem grows only slightly bigger makes for exponential growth in the time needed to solve. So the polynomial time solvable problems are the problems which you can solve without searching. That's the key part. Those are problems like multiplication, where you don't need search. Now, the NP problems on the bottom half of the slide are the problems where you can quickly check the answer. Not necessarily quickly solve the problem, but if somebody gives you the answer, like someone gives you the factors, which might be hard to find, but if someone gives them to you, you can quickly check that they work just by multiplying them together and seeing if you get the number you're trying to factor. So the NP problems are the problems where you can quickly check the answer, even though you may not be able to find the answer quickly. And that includes the search problems that are interesting to us, like the clique problem, where if you have a clique of a certain size, you can actually check that that clique is there. Or the factoring problem, you can check that you actually have the factors, even though finding those objects may take a long time. So the easily checkable problems, all these NP problems, these include all the searching problems. Okay, so the P problems are the problems that you can solve without searching, and the NP problems include all the problems that you can solve even with searching. So now, if you draw this as a Venn diagram here, here's the NP problems. These are the problems that you can solve even with searching, and the P problems are the problems that you can solve, by avoiding searching. These are the easy problems and the easy checkable problems. So they form a nested Venn diagram like that, where the NP problems include like the factoring and the clique problems we described, and the P problems include, for example, like multiplication or sorting. These are easy problems that don't need search. And the question is, if every one of the problems that needed searching, so all of these NP problems are the problems that need searching, that involve searching, if you can solve them all without searching, then P would equal NP, because the NP problems would all be solvable without searching, and so that they would be reduced to P problems. So it's possible that these two classes, which I've shown here as being different, they actually might become the same, or they might actually be different. And if they were the same, that tells us that you never need to search. You can solve problems without searching. Or if they're actually different, then that tells you you do need to search sometimes. Sometimes search is unavoidable. And so the question of whether P equals NP or P is different from NP is not known. So that's really another way of precisely saying the question of, is searching necessary? And it just gives you a precise counterpart to that. But the thing that you should have in your head is this problem about, is searching necessary? That's really at the heart of what we're talking about. Or, is searching sometimes unavoidable, or can we always avoid searching? And that the answer to that is beyond present-day mathematics. So in terms of the history of this problem, in the mathematical literature, it goes back to the 1960s, when people first started formulating what it means to solve problems in a certain amount of time. And then it was precisely formulated in terms of this P versus NP that I just described, and the companion notion of NP-completeness that we will talk about in a few minutes. So that was, the precise formulation came out in 1971, so it's been a while now. Almost 50 years, in fact, since that problem was precisely formulated. And now we have, what's remarkable is that what was discovered in von Neumann's archives is that the great logician Kurt Gödel had written to von Neumann a letter which really contained the whole essence of the P versus NP problem in that letter. So it really goes back even a little bit further. And let me just show you quickly that letter, which is kind of, just because it's such a cool bit of history in the subject. Here is his 4-page letter that Gödel wrote to von Neumann in 1956. I'm not going to read it to you because, for one thing, it's in German, but I'm going to highlight a few little key phrases of that letter. But before we do that, let's just remember who these two people are. Kurt Gödel lived in the early part of the 20th century. He was considered to be the greatest logician of the 20th century. Some people say he was the greatest logician since Aristotle. And he proved some very important things about mathematical logic in the 1930s. Later, in the 1950s, turning his attention to this complexity problem, which is kind of remarkable because it was really just at the very beginning of computers as we know it today. John von Neumann was alive in the earlier part of the 20th century. He was a very broad mathematician, worked in both in pure math and in applied math. He also was involved with some of the earliest computers. And in fact, people call our current architecture for computers the von Neumann architecture. Now, getting back to that letter briefly, here was highlighting a few of the phrases from that letter. Gödel is writing to von Neumann. He says, "Lieber Herr von Neumann," in translating the German into English, "Dear Mr. von Neumann," written here in Princeton, 20th of March, 1956. Just as a little bit of a curiosity, both Gödel and von Neumann were members of the Institute for Advanced Study in Princeton at that time, in the mathematics building, presumably down the hall from one another. Why Gödel would have chosen to write a letter to von Neumann instead of just knocking on his door is unclear. It was well known that Gödel himself was kind of a quirky guy, very, very awkward and shy, maybe didn't feel comfortable talking to the very famous von Neumann. Or it was also the case that von Neumann was quite sick in 1956. He was dying of cancer, and he died within a year of the receipt of this letter. And in fact, the first page of the letter, Gödel refers to von Neumann's illness and hopes that he gets better. But then he goes on to say, starts to talk about mathematics, and he's interested in the problem of how much time does a computer need to test if a mathematical theorem has a proof of a certain length. As a consequence of Gödel's work, it was known that it was not solvable by computer whether a mathematical theorem has a proof at all, but having a proof of a certain length is something that you can solve on a computer because you can just try all possible proofs and see if one of them is actually the proof of the theorem. You can try, I should say, you can try all possible proofs of a given length because there's only a finite number of them. But the thing is that gets you to a brute force search because the number of such proofs of a certain length, though finite, is very large. And so it would take you a vast amount of time to go through them. And Gödel is asking, how long would it take a computer to go through all proofs of length n? And so for an optimal machine, how long would that take? And then he goes on to talk about doing exhaustive search or not. And then he goes on to talk about other problems besides testing whether a statement is true or not, such as the primality testing problem, and how in general the number of steps in finite combinatorial problems can be reduced. Looking at this letter with our current perspectives, one would have to say that it's quite remarkable that Gödel had come up with this notion back in 1956, which was really a foreshadowing of the work that had come much later. So just a testament to him as a real visionary in computer science and mathematical logic. Anyway, so he goes on to sign it, Kurt Gödel. And now, since those early days of the P versus NP problem, it has become a very famous problem in mathematics. Some of you may know that in the year 2000, to celebrate the millennium, a committee of mathematicians was brought together to pose or to highlight the most famous unsolved mathematical problems of our day. And they came up with a list of 7 problems. And as you can see, the second one on that list is the P versus NP problem. So within the mathematics community, the P versus NP problem is considered to be one of the great grand challenge problems of mathematics. Now, one of those you may notice has a check mark instead of a bullet next to it because one of those 7 problems has already been solved, so-called Poincaré conjecture. But that's outside the scope of my talk. So just to mention that P versus NP is on this list of problems. And not only would you get fame and glory for solving any of these problems, but you'd also get $1 million because there's been the businessman, Langdon Clay, has offered a bounty for the solution to any one of these problems, namely $1 million. Of course, if a mathematician doesn't care about the $1 million as much as he would care about, just solving the problem itself. Now I've thought about the P versus NP problem over the years, and so I do get people claiming to solve it, sending me emails and letters with proposed solutions, basically people think it should be easy to solve this P versus NP problem because it should be easy to show that you really need to search for some of these problems. Because it seems almost obvious. I mean, how are you going to factor big numbers without looking for the factor? Well, here's just to give you a flavor that there might be other more clever things you can do. For example, if you want to test if big numbers are prime, you can do that more efficiently than looking for all of the factors and seeing that a prime number doesn't have any non-trivial factors. How does it? I'm not going to go through this in detail, but just to give you the flavor of it. Here's how you can test if large numbers are prime without going through a brute force search to look for factors. And it relies on an old theorem due to Fermat. It's not as Fermat's last theorem. It's the same Fermat, but this is a different theorem for which he actually did have a proof. It's called Fermat's little theorem, and it's just a very simple statement. It says if you have a prime, we'll call it P, and you have some number between 1 and P minus 1, so listed here is A, so you have prime P, and you have a number A, which is less than P, between 1 and P minus 1. Now you take that number A, and you raise it to the P minus 1 power. We'll do an example in a second, but you take A and you raise it to the P minus 1 power, just the ordinary sense. And then you divide by P and take the remainder. Okay, you got that? Take your number, whatever it is, any number between 1 and P minus 1. You raise it to the P minus 1 power. You divide by P. You always get 1 for a remainder. It's not obvious that that would be true because you might get any value between 1 and P as the remainder. But in fact, you always get 1 as the remainder. Let's do it in a quick example. So if we take the prime as a, you can do this yourself. You can try some examples, but let's take the prime to be 7. A, which is a number between 1 and P minus 1, so we can pick it to be anything. Let's say 2. We take 2, we raise it to the P minus 1 power, so that's 2 to the 7 minus 1, or 6. So 2 to the 6th power. That's 64. And now you divide by the prime, P, which is 7. So you take 64, you divide by 7, and you look at the remainder. That's a so-called take 60. Take that, the number 64, and look at it mod 7, as we say. So take 2 to the 6th power, which is 64, divide by 7, take the remainder. You get 1, because as everybody knows, 7 divides evenly into 63, so when you have 64, the remainder is 1. Okay? So this is just an example, of course, not a proof. But you can prove this thing, and it works for every prime and every A, within the range. Now, let's try see what happens if you have a non-prime. Let's say the number 15. As we know, 15 is not a prime. Again, let's take A again as 2. So now we're going to raise 2 to the 14th power. We get this number 16,384, 2 to the 14th power. And now we divide by 15. because that would be plugging in, a non-prime into the same equation up here. And now, so you take the remainder after dividing 16,384 by 15, and you get 4. You don't get 1, which is what the theorem says you have to get if P were prime. So you get 4, you don't get 1. Now, what that tells you, this is the cool part. This tells you that 15 cannot be prime. That you got 4, so 15 couldn't be prime because if it were prime, you had to get 1. And the fact that you didn't get 1 is a proof that 15 is not prime. And it's a proof that doesn't tell you what the factors of 15 are and doesn't rely on finding the factors. It just relies on showing that P doesn't have a property that all prime numbers have. And in fact, you can do this calculation vastly more quickly than you can do the calculation of brute force search for looking for factors. Okay, so let's. So let me get on. I mentioned to you this notion of NP-completeness at the beginning. So this is really, in a sense, the only real progress that has been made in trying to understand whether or not P equals NP. And there's a kind of a cool fact that tells you that the factoring problem and the clique problem actually are related to one another, even though they superficially look different. And that is and more precisely, if somebody finds a way of solving the clique problem without searching, then it gives you a way of solving the factoring problem without searching, even though the two problems look like they have nothing to do with one another. And that's because of this notion of a transformer, that there are ways of converting factoring problems into clique problems, so that if you can solve the clique problem quickly, that allows you to solve the factoring problem quickly. Kind of, as shown pictorially by here, you feed in that problem you want to factor into this transformer, and it produces a clique which represents that factoring problem, in terms of this clique, so that if you find a clique problem, if you find the clique, that actually will give you the factors. Not obvious how you do that, but it's in fact that can be done for any NP problem. And so clique has this feature that it's kind of the granddaddy or the grandmommy of all of these NP problems, in that if you can solve that one problem without searching, you can solve all of the NP problems without searching. Kind of amazing fact. This applies to games as well, without getting into the details there. I don't want to overrun my time. Complexity, just to give you sort of a little taste of where the field has gone. We have, P and NP. There are other complexity classes based, for example, on how much memory you might want to use. So over the years, people have discovered a whole rich classification system for different kinds of computational problems that reside in different places within these within this classification. So it's almost like a periodic table of complexity. Here's the primality problem, which is now solved to be in polynomial time, as I mentioned, but that was only shown in 2002. Before that, it was in a slightly larger class called RP, for randomized polynomial time. Anyway, without getting into all that, just to give you a flavor that the field is a very rich field, getting back to the famous unsolved problem of P versus NP, is searching necessary? Just to give you a taste of how one might actually go about trying to solve this great mathematical problem. One thing that people have tried is to understand, clever algorithms, for solving problems like the factoring problem or the clique problem. It's conceivable. Most people believe that there's no fast way of solving those problems, that you really need to search. But in order to prove that, you have to show there's no clever way of doing it, that there's no way of avoiding the search via some clever algorithm. Now, how are you going to do that? Well, the class of clever algorithms is a very rich class, and that's part of the reason why no one has been able to show that there isn't a clever way of solving these problems. How would you show there's no clever way of factoring big numbers? That you really just need to search for the answer. How would you do such a thing? Well, one way that people have done, and this is a typical mathematician strategy, is if you can't solve this really hard problem, let's try to make the problem easier. And the way we've done that, so here you think of the computer as sort of this devil coming up with these clever algorithms. Suppose you limit the computer's capabilities by handicapping it. So now the computer can't function with as rich a set of possible algorithms as it might before. So you limit the class of algorithms. You could maybe call it a handicapped computer. And then you try to solve, well, at least for the handicapped computer, it has to take a long time because the computer can't run anymore. It can only limp. It can only walk. Or maybe if that's not enough, you hit it again, and now it's got both legs handicapped. Now the computer can only crawl. Eventually, with enough handicaps, you can show that the computer has to take a long time, say, to solve the factoring problem or other problems like that. And then the idea would be to eliminate these handicaps, maybe take what you've learned by understanding the handicapped computer and try to reduce the handicaps to show your understanding applies for more general computation. So that would be the idea, but it hasn't yet played out to allow us to solve this problem. Another possibility would be another sort of approach would be let's try to find an input, an example like a number to factor or a clique problem where you want to find the clique, which is particularly a difficult one where you really it's going to really tax the computer to solve that particular instance. It's natural to think that, well, you want to look at larger and larger problems because the complexity is going to grow as you look at very large problems, and maybe even perhaps taking that to its extreme, kind of finding infinite problems. And maybe if you could formulate, and this has been done, formulate infinite versions of these problems and infinite computation. Maybe you can learn something about what the capabilities of the computer are sort of in that sort of infinite world, and that can sort of give light into the finite world. Again, all of these are strategies. None of them have succeeded yet, but we hope that they will someday. So will the P versus NP problem ever be solved? Hard to say. We certainly need new ideas. And that's the end of my presentation. I hope you enjoyed it, and we now can turn it over to any questions if any of you have any. I will do my best to answer them.
If you have any questions, feel free to add something into the chat.
What is an example of an optimal game? Okay, thanks for that question. One way, I'm not completely, let me answer your question this way. Maybe if I'm not getting at it exactly right, please just refine your question. But if you want to find an optimal strategy for playing a game, you can just brute force your way through the entire game tree. So you can say, imagine, chess as an example. You want to know, does white have, under optimal play, would white win? Or maybe black would win, or maybe it would be a draw. So what you could do is you could try every possible move for white, And then for every one of those moves, you try every possible response for black, and then every possible response to that for white. And you just keep going down the tree of possibilities. And then, when you get to the leaves where one side or the other has won, you can then propagate back up from that and understand where the forced wins occur. And that will work in principle. The only problem is that the tree for chess on an 8-by, the standard game of chess on an 8-by-8 board would have the size of the tree be bigger than the known universe. So it's hopeless to try to imagine searching through that, an astronomically large tree. So that's, we can, there is a lot of mathematics around these games that has been shown, and complexity results as well. And no one knows whether there's a more efficient way of solving chess or these other games that doesn't involve searching through some enormous tree. So what's the difference between NP-complete and NP-hard? Okay, now we're getting to a little technical here, but that's fine. An NP-complete problem is, as I described, that's a problem that's a problem that's in the class NP, in that you can easily verify the answer if someone presents it to you, and you can transform any other problem in NP into that problem quickly. So an NP problem has two features. It's in NP, and it has everything else in NP, it's reducible to it, so-called. Now, an NP-hard problem only has the latter. It may itself not be in NP. So it might be outside of NP, but as long as everything else in NP is reducible to it, then it's NP-hard. So said another way, NP-complete is equivalent to being NP-hard and a member of NP. So can I turn the clique problem into the factoring problem? That's a great question. As we described, you can convert the factoring problem into the clique problem. It's not known whether you can convert the clique problem back into the factoring problem, where you can, in general, convert clique problems into factoring problems. That's an open question. So the question of whether factoring itself is NP-complete is not known. But the clique problem is known to be NP-complete, because you can transform any NP problem into the clique problem. So how much time is considered long for a computer? Well, I mean, that's, again, it depends on how much time you have. For some problems, it might depend on how important the problem is. If you want to crack some code, and it really, somebody's life depends on it. So, for example, there were codes that were cracked during World War II. The famous Enigma code was cracked by Alan Turing's group in England, and this played actually an important role in World War II. They partially solved it. They didn't completely solve the code, but they solved it well enough that they could reduce the search time to a manageable level. And it was worth it to them to invest the effort required, and they built special purpose. In those days, there was not electronic machines, they were mechanical machines. But they built special purpose tools to help them search through the keys for solving those codes. So there's no firm answer to what's considered long or not for a computer. It really depends on the application. So how do you find out how long it takes for a computer to do a certain job? So for how long it would take to factor a number? Well, so I'm answering Nerdy's question, Nerdy Genius. That's actually, doesn't sound, I don't think that's your real name. How long would it take to find out how long it takes? How do you find out how long it takes a computer to do a certain job? Well, I mean, I could tell you by analysis how long it takes an algorithm. Maybe there are, so if you're given a particular algorithm, by analyzing that algorithm, you generally can figure out how long that particular algorithm is going to take. But in general, how long does it take to solve some problem? Well, I mean, that's really another formulation of today's question. I mean, how long does it take to solve the factoring problem? If that were polynomial, then I would have solved P versus NP for factoring only. It was so that factoring doesn't require searching. So, you know, if you could tell how long it takes computers to solve particular problems, then you can answer these questions that I'm posing today. So no one knows how to answer that. Only analyzing particular algorithms, that's what people know how to do. Now, how might one start studying complexity theory? What kinds of mathematical prerequisites are there? That's a very good question from David Kick. Thank you. Well, the kinds of mathematics that is used, I would say as a starting point, there's a branch of mathematics called combinatorics, which has to do with, graph theory, counting problems, permutations and combinations, which you probably have run into. And then it goes on from there. It's a very rich subject. There's a subject called Ramsey theory. Lots of very interesting mathematics that comes up in the study, basically of finite sets. That's what this combinatorics subject is about. And I would say beyond that, the mathematical logic is helpful. And also algebra has turned out to be coming up increasingly in many parts of complexity theory. So that's another area that I would study. Incidentally, I'm not trying to market anything here, but I have written a textbook in this subject as well that I teach this course. I'm going to be teaching it in the fall, in fact, online. And I use a textbook that I've written. So that gives you could look at that as well and get a sense of what the subject is about. It really pretty much starts from the beginning. So you could get the flavor for it by at least looking through that book. But these are all great questions. Thank you. Would I be surprised if P versus NP is solved in a couple of years from now? I would have to say yes. So would I be solved if the P versus NP is solved soon? I can tell you I have a little bit of personal history in that. I first learned of the P versus NP problem as an undergraduate in the early 1970s. Then I became a graduate student in the latter half of the 1970s. I became very interested in the P versus NP problem, as were many of the other graduate students in computer science at Berkeley, where I was a graduate student. And one of them, a guy named Len Adelman, made a bet with me. I bet, this was in 1975, that the P versus NP problem would be solved by the year 2000, which seemed like way off in 1975. I made a bet with him. It was a bet for an ounce of gold. And in fact, I sent him a gold eagle in the year 2000 to pay off because it had not been solved by that point and still remains unsolved. And so I'm not making any more bets on the outcome and the time frame for P versus NP. I hope I get to see it in my lifetime because I have spent a lot of time thinking about it, and I'm just curious to know how the answer would go. I hope to solve it. I hoped and still hope. I think about it at times that maybe I'll make some progress on it, but it's a very hard problem. It's hard even to know how to begin, really. But it's a great problem. Really great. It's a really great problem. Anything else? Guys, thank you for coming to listen to me.
Okay, that's it. Thank you, Professor Sipser, and let's give Professor Sipser a round of applause.
Thank you, everybody.
All right.
Online applause. Well, you're welcome, everybody, and thanks for coming. Okay, bye-bye. Good luck with the rest of your lectures.
Thank you.